Okay, last session we started with compression, deep compression, which is about compressing neural networks with three methods: pruning, quantization, and Huffman coding. Pruning was very simple. Basically, the idea is that these neural networks are usually overparameterized, and one observation is that many of them are close to zeros. If that's the observation, many of the weights have values close to zero. If that's the observation, then probably we can actually set them to be equal to zero, force them to be zero. And that's called pruning. And once you force them to be zero, your matrices are going to end up being sparse. And for sparse matrices, we can do sparse linear algebra, and there are efficient ways to do arithmetics on those types of matrices, as well as efficient ways to store them. For instance, you can have compressed sparse row, CSR, and CSC. These are two types of methods. And as you can see, the number of numbers that you're going to need to store is directly related to the number of non-zero elements. So rather than storing n squared terms, if your matrix is, if you have a square matrix with size n, you're going to need n squared numbers. Now you're going to need much fewer numbers to store. So this is what we covered last session. Actually, to further, there is one problem. You need to still store the indices, because you're going to tell at this index, I have this number, this floating number, or this value. But then because these are sparse, you need to store the indices. The idea is that rather than storing the indices, you can actually store the index difference rather than the absolute position. And for convolutions, we are going to use 8 bits. And for fully connected layers, we are going to use 5 bits to store the weights. But what does it mean visually to store the index difference? These are the absolute values of the absolute positions, 0, 1, 2, 3, 4, 5, etc. Rather than storing, for instance, 15, you can store 3. So how does it work? Let's say at the first index, you have a value of 3.4. Then the next non-zero entry in your array, because matrices, you can actually represent them as an array. That's how they are represented in memory. So you have an array of consecutive numbers. The next time that you have a non-zero element, it's at position 4. You need to store 4, because 4 is less than 8. So you're still allowed to store that number. But then the next non-zero element is appearing at 15. And what's the difference? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the difference is bigger than 8. You're gonna put a dummy value here at the 8th position. You fill it with zeros. And then the next one is easy, because you can store the difference as a number 3 rather than number 15. So this way you're making more efficient use of the memory by storing in indices differences. Is that clear?
How much more efficient is this?
How much more efficient is this?
In memory complexity, I guess.
Actually, that depends on how unlucky you are. If you're really, so usually the way that these types of analyses are done, they're gonna do worst case scenario or best case scenario, and then there is gonna be an average memory consumption when things are random to take the expected value. And what are we taking into account? We might be really unlucky, and each time our indices are by one number bigger than the index difference, where you have the non-zero element. First, you have a non-zero element here, then you're unlucky, and the next non-zero element is at 9. Then you need to store an extra 0 here, okay? Then the next time you're going to be again unlucky, and this one is going to be, I don't know, at position difference 9. Then you're again storing a filler 0, and then that's going to be really bad. But on the other spectrum, on the other end of the spectrum, you might be really lucky each time, and all of these values are less than 8. I'm not actually sure if that's the best case scenario. There is also another case that these numbers are randomly treated, and then you have to take expected value. So I don't know the exact answer to your question of what is the exact efficiency that you're going to get out of it, but it's definitely more efficient than storing these numbers. 15, and then you have to store, I don't know, 1001.
And then I guess a sort of different question is, when you actually multiply one of these structures in hardware, do you have to turn it into a regular sparse matrix first?
No, this is just for storing the indices.
Okay.
So the way the algorithm works is that whenever it sees as filler 0, because we know that in our matrix, we are not going to see 0 because these are sparse. We got rid of the 0 by pruning. So whenever you see a 0, you know that the index is the addition of 8 plus this current value. So you can just read it off. Just one more operation.
Okay, I see. Thank you.
Any other question? So that's for pruning. How do you quantize your weights? So pruning is going to save you 9 times or 13 times less in terms of the parameter. The next one is really interesting. It's giving us a boost in terms of reduction. That's actually very good reduction. So how are they achieving this? The idea is weight sharing. And if you think about it, weight sharing is at the core of convolutional neural network. And it's actually at the core of deep learning in general. We were sharing weight when we were doing convolution, and we were sharing them by sliding a window over our pixels, over the entire image. And the parameters of those small windows were shared among all of the windows that you're going to slide over an image. For recurrent neural networks, you're going to do weight sharing, and you're doing weight sharing over time. You use the same weights and biases from one time step to the next one. Now you can use the idea of weight sharing to quantize your network. How is that going to happen? You have a bunch of weight. The blue ones, if you look at them, they're really close to 2.09, 2.12, 1.92, 1.87. So these are closer to 2. The green ones are close to -1. The orange ones are closer to 0. And these ones are close to 1.5. What you're going to do is you're going to do a clustering algorithm on these values, and you're going to end up with 4 centroids for your cluster. And the clustering algorithm is actually, for this example, is going to give you 2, 1.5, 0, and -1. You still need to store the cluster indices to know where your weights are actually residing. For instance, 3 is corresponding to this location, that location, this location, and this location. And -1 corresponds to the 0 location. And the idea is that all of these blue values, you're going to assume that they are 2. All of these orange values, you're going to assume that they are 0. And all of the green ones, you're going to assume they're -1. So what's the difference? Initially, you have to store 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 numbers. And each one of them are floats. They're going to take up 32 bits of your memory. Now what you're going to need to store is a 2-bit unsigned integer for the indices and 4 floating numbers. So that's what you're going to need to store. And we are going to treat convolutions and fully connected layers differently. For convolutions, we are going to use 8 bits, which is going to give you 256 centroids, and 5 bits is going to give you 32 centroids for your fully connected layer. And before I go into more detail, can somebody tell us why we're treating convolutions different from fully connected ones? Why do we need less bits? Why do we need fewer number of centroids?
Convolutions are already smaller in data, so we can get away with using more bits because it'll process this.
Can you say it again? Sorry, my volume was low.
The fully connected layers are larger generally than the convolutions are, and so it is more costly to store them with high accuracy.
That's one reason. And there is also another reason. Parker is saying are CNN parameters more sensitive? That I'm not sure, but I'm looking for another answer. If you think about it, quantization is similar to pruning. Pruning, we were setting the values that are close to 0 to be 0. Quantization, you are setting the values that are close to 2 to be exactly 2. So you are somehow sparsifying your matrices. You're making them sparse. So knowing that, what's the difference between the convolution and the fully connected? Like convolutions, less unique values to store. You're sort of close.
The fully connected layer is more dense to begin with.
Exactly. So fully connected layers are more dense to begin with compared to convolution. Convolutions are at least sparse in space. Maybe in channels, they are not sparse, but in terms of a number of filters, they are not sparse. But in space, they're already sparse enough. And if we go back to Parker's answer, it means that those parameters are actually, if you think about it, more sensitive. They are carrying more information with them. So I think we are all on the same page. But let's see how much we are saving and what is our compression rate. We want to see how much we are compressing if we go from this setup to storing only the cluster indices and the centroid. How much are we saving? If k is the number of your clusters, in this case 4 of them, and log2k is going to be the required bit to encode the index, because we are using a 2-bit, and this 2 here for the log is coming from that. That's the required bit. And then we are storing n numbers. These are the numbers that we are storing. For instance, we are storing 16 numbers here. We need to store 16 indices. So this guy is going to be 16. This guy is going to be 16. Log 2k is for representing these numbers, 0, 1, 2, and 3. K is the number of centroids and the number of clusters that you have. In this case, it's 4. And b is the number of bits. If you are using float 32, that's going to be 32 bits. And for that particular example, this is the math. So you have 16 numbers. Each one of them is 32. This is the amount of memory that you're going to need to store this weight matrix. You still need to store 16 numbers, but they're going to cost you less because these are 2-bit. Actually, this 2 is coming from taking the log of 4 with base 2. That's going to give you 2. And then you're going to need to actually store 4 centroids. Each one is going to take up 32 bits. And this is the compression rate precisely for this particular example. So doing that, you're saving 3.2. But we know that we are going to use 8 bits and we are going to use 5 bits, and we have much larger weight in our network. In the end, the reduction is going to be of this sort, 27 times up until 31 times. That's the compression rate. That's how much smaller your network is going to end up being. How do you find the centers and the centroid? You do k-means. Let's see a high overview of k-means clustering algorithm. You start with n original weight. In this case, you had 16 weight. These are these W1 up until W16. We want to have only 4 centroids, or we want to have k clusters. K is much less than n, and we don't know the values of C1 up until Ck. What is the objective function now? If you want to write an objective function, you want to minimize this objective function, which is basically within cluster sum of the squares. It's the sum of square differences between your clusters and your weight. And the way that you typically solve this problem is using expectation maximization. There is one expectation, which is basically taking the mean of the cluster, and there is a maximization step. So that's a EM algorithm, and that's going to give you 4 centroids. So is everything clear? We knew that these are close to 2, but we need an automatic fashion of figuring that out. And that's how k-means is going to come to rescue us. Are there any questions so far?
Is this very sensitive to the clustering algorithm you use?
Not really.
Cool.
What's this diagram? Well, I guess my first question is these centroids that we calculated here just so happened to be like multiples of 0.5, but in general, they'll be as precise as whatever 32-bit or 64-bit or whatever you're using for your floating point numbers.
Exactly. So yes, these are going to be values that you're going to represent.
And in this case, they were just kind of cooked up by hand to have a really clean average of 2 and 1.5 and 0.
Yes. So this is a toy example to illustrate the concept. But yes, you're right. Usually this K is going to be of the order of 256, not 4 of them.
Yeah.
And N is going to be usually huge, the number of scalars in your weight.
And do we learn this per channel, or do we learn this for the entire set of weight matrices?
You learn it layer-wise.
Okay. And then last question, this fine-tuned centroids diagram, like what is the stuff at the bottom with the 0.4 and 0.2 and 0.04 and negative 0.03? Yeah.
Great question. That's where I'm going next.
Okay.
If you stop here with the centroids, yes, you compressed your network, and we had a comment last session that this is going to be lossy, which is a very valid comment. Before I go forward, there is a question on the chat. Do we pick the number of centroids? And if so, how? Yes, so we pick K, and we pick it to be, for convolutions, to be 256, and for fully connected, we pick it to be 32. K is 256 for a convolution, and it is equal to 32 for a fully connected lake. Does that answer your question? I would imagine one driving factor is the target network size.
Like if we're trying to cram this network onto a certain piece of hardware that only has like so much memory and whatnot, then you could pick your clustering to fit it onto that target sort of.
Yes, that's a valid comment. The idea is that in the end, you want to put this network on a mobile device, and there is only so much memory that's available on that device. It means that you're going to have different compression rate, and the compression rate is going to specify K. But for now, we are going to do 256 and 32, and that's how you're actually reporting this reduction in space. But then the paper has another objective. They don't want to just reduce the amount of computation and storage. At the same time, you want to maintain the same level of accuracy. Once you do this step, you're going to lose accuracy. Now we're going to retain the accuracy. It means that we are going to do a little bit of retrain. Now the question is, how are you going to retrain? How are you going to backpropagate your errors through the network? And here are the details. You have your loss function. You're taking the derivative with respect to the centroid, and let's say you have K of them. So you're doing the derivative of your loss function with respect to this centroid. And that's exactly these values that you have here, which is going to help you fine-tune your centroid. But how are you going to end up with these values? You use chain rule. You take the derivative of your loss with respect to the weights of the original network, which are these numbers. These are going to be the gradients. And then you're going to read off from this index and say all of these blue ones should be grouped together together. All of these orange ones should be grouped together. All of these green ones should be grouped together. That's what this one here means. That's an indicator function. It's going to pick up the corresponding color in our example. And then there is a summation here. That summation is the reduction to give you these gradients. Once you have the gradients, you can update the centroid and do your training. So that's how you train your quantized network. And the objective is to maintain the same level of accuracy. So does that answer your question? Now we know what are these numbers.
Sorry to pile on the questions. Does this also reduce, can you move to a lower precision number as well for the centroids and the gradients and stuff?
Probably for the gradients you could do that because these are usually small numbers and probably there is a way to reduce it even further. But in the end, we don't care about the gradients. Why is that? Because we don't store them in the end. On the target machine, you're just going to store the forward pass of your network. Even here, it's okay to store the actual gradient during training. And it's actually what the paper is doing, what the algorithm is doing. You're free to store this while training. But once you're doing inference, you're storing the centroid and the cluster indices. Does that answer your question?
Yeah, it does. But I guess I'm wondering if, maybe even at forward pass time, can you do this all in FP16 instead of 32? That itself is like some kind of quantization, right?
Yes. There is this feature that you can train your network with mixed precision. So the word that I want you to search in Google is automatic mixed precision. It's a technique for training neural network on modern GPUs.
Okay. Yep. I found it.
But it doesn't have anything to do with this paper, okay?
Okay.
The idea of this paper is about weight share. And that's what they mean by quantization, is that you are sharing your weight. They don't mean that you store, rather than storing 32 floats, you're going to store 16-bit floats, etc. Okay?
Okay.
Any other question? Because these modern GPUs have another feature, and that's called tensor cores. And tensor cores are mostly 16-bit. And for that, you're going to need automatic mixed precision. Okay. You can even save more by doing Huffman coding. What is Huffman coding? Huffman coding means it's very simple. You do a histogram of your weight in the end. Some of them are going to end up being more frequent than the other ones. The ones that are more frequent, you can store them with fewer bits. And this way you're saving in terms of storage. And in the end, after all of these operations, you're going to be able to reduce by 35 times up until 49 times. So Huffman coding is not hard.
I have a quick question about that.
Yes.
So Huffman coding makes sense to me if you're doing if you're using an alphabet and you're using fewer bits to represent more common letters.
Mm-hmm.
But wouldn't the number of bits in this scenario be dependent on the value of the weight? The weight requires all 32 bits. Then how do you reduce that?
So all you need to store are your centroids. You're going to make a histogram of the centroids, and some of these centroids are going to be more frequent than others. The ones that are more frequent, you can store them in fewer bits. It's not necessary that all of them are 32 bits. All you need your computer to know is that this piece of memory corresponds to, I don't know, number 2, which is the most frequent one. And for that, you can actually use 2 bits. Does that answer your question?
Well, so what if the most common centroid is some number that takes up, all 32 bits? I don't know. I guess it doesn't have to be answered right now. I can just look into it on my own. But
I think you're saying that I'm stuck with 32 bits because I want to represent this number as accurate as possible in 32 bits.
Yeah, and
But all you need to have is a mapping from your memory to that number.
Mm-hmm.
And that mapping, you can actually assign it in an efficient way.
Mm-hmm.
Because all you need is just reading of those numbers. Okay, this piece of memory is actually representing 2.0000789. Okay, it's just a representation.
Okay, I think that makes sense.
So is it the same concept of pointers, the same concept as pointers? So yes, when I was mentioning mapping, the way that you represent them is you use pointers to represent. So the input symbols for Huffman coding are the centroid indices we are using for our parameters. So yes, the way that you're using Huffman coding is for the centroid. You do a histogram of your centroid and then represent the ones that are more frequent with lower bit. It's across the whole network, right? You're encoding each weight using a master dictionary. Yes, the way that you do it is you create a histogram of all of your weights, all of the numbers that you need to represent, and then you represent the most frequent ones with less bit. Yes, it's gonna be one dictionary for the entire net. Any other questions? So would it be something like if the most common number is 32 32 in our data, we would have a dictionary with 32 being 0 and represented with a single bit. Then just keep going for all the numbers in order of how often they occur. That's perfect. That's the perfect way of putting it. You don't need to represent 32. You need to represent 0. And for that, you're going to need very few bits, okay? And that number 32 could be a pi, which you can actually represent it with a bit if that's the most frequent number in your dictionary, in your data.
So it seems like this gives you more reduction in storage the larger your network is.
Probably, and at the same time, you need to look at the distribution of your weights. If all of your weights, because of your training data, are of the same order, they have the same histogram. I mean, your histogram is uniformly distributed, then Huffman coding is not going to save you much. So these are complicated stuff because now some information from your training data is being transferred to your weights. Now we are looking at the weights and looking at the histogram of the weight. Does that answer your question?
Yeah, that does.
I think there is some confusion here. You might say that to represent a number like pi, you're going to need a lot of floats. Not necessarily. This is relative to the distribution of the other number in your data set, in your weight. Then you're going to find an efficient way of representing. It's just a representation. Any other questions? We are going to see this Huffman coding idea when we do natural language processing later. Okay. What did we actually save? Sorry, the figure is small. Do you see it?
Yep.
You can do singular value decomposition of your weight, and that's going to give you some saving, but at the same time, you're losing accuracy. This is how much accuracy you're losing. For instance, let's read off this number. You're losing a little bit less than 1% in terms of accuracy. If you do quantization only, depending on the amount that you're compressing, this is the compression rate. Initially, you're not going to lose much accuracy, but then it's going to drop more and more. So anything more than, if the size of your resulting network is, I don't know, is this number 6%? With around 6% of the one that you started with, you're losing a lot of accuracy. But if it's 8% or 14% or even 16%, you're not losing much. With pruning only, this is how much you're losing in terms of accuracy. But when you do pruning and quantization and these techniques and do your retraining, you can keep only 4% of your network or 3% of your network and still be as accurate as the original AlexNet. So this is impressive in terms of saving. Any questions? It seems like this compression accuracy relationship could vary greatly between architectures and training data. Has this been studied? You are right. It could vary a lot between architectures and training data. And has this been studied? I know that the paper that we are going through studies it for AlexNet. I don't know about other networks. Actually, that could be a very good project if somebody wants to spend some time on it. You can take, I don't know, ResNet or AlexNet or GoogleNet or VGG16 and see if you follow this process, can you make a similar plot and try to study that. And you don't need to worry about the technicalities of how to store sparse matrices. You just assume that they are 0. Don't worry about it. Just worry about the accuracy. Don't worry about the index difference, and don't worry about storing these efficiently, the centroids and the cluster indices, but just try to test the idea that do you lose accuracy or no, and how is it dependent on the architect and training data. I think we are out of time for this session. For those of you who have questions, you are more than welcome to stay and ask. And for those of you who want to leave, you are more than welcome.
Let's see. I have a comment. Let's see. I asked if this was lossy last time, I think. And see, I understand now we're controlling for the behavior of the networks. And that is what we are seeking to preserve when we compress them. But now I'm wondering if this compression changes the way they classify images incorrectly. So maybe I give my original network a soccer ball and it incorrectly classifies it as a cactus. I wonder if after compression, it may incorrectly classify it as something else.
So yes, that's now you're talking about a single example in your data set.
Right, but because it was incorrect, we don't necessarily care about how that was classified.
And you're saying that accuracy is not giving you that information.
Well, isn't the accuracy the percentage of images that we classify correctly?
Yes, but you said my original network was classifying a ball incorrectly, and now my new network is classifying it to something still incorrect, but not a ball, a cactus.
Correct.
But that thing is not going to show up in your accuracies. For accuracy, you're counting the number of correct, basically true positives, divided by the entire size of your data. That's your accuracy.
Mhm.
But yes, you are right. Maybe accuracy is not the correct metric to look at here. Maybe you're actually losing some information, which is not showing up in your accuracy. For that, I don't think the paper has done it, but you can look at the confusion matrix before and after compression. That's going to give you more information.
You could even look at a heat map of the difference between the confusion matrices, and it would highlight exactly what effects that caused, exactly which differences have been exposed.
Yes, exactly. So I think these are really good exercises. The network is trained. Pruning it shouldn't be that hard.
Yeah, that sounds interesting. Thank you.
And you can actually look at the heat map, the difference between confusion matrix.
I was just thinking of if you built a matrix whose weights were the difference between the exact weights and the quantized, and then see what that thing knows, you could like measure the information loss, but that's not quite true because of all the nonlinearity, right? Building a matrix with all of the small little differences as weights is not the same thing as feeding forward through both networks, the quantized and the full network, and then looking at the difference afterward.
No, because if you look at the weights, it's hard to interpret them.
Yeah. So I had an unrelated question. It seems like the pruning and the quantization are both lossy compression in that, like, it says same accuracy on this diagram, but technically it should be like, I don't know, like 1 minus epsilon accuracy, where you get to control that. But then Huffman encoding is lossless, right?
Yes.
Okay. So is that why there is this range, like 9 to 13 and 27 to 31, because different networks are going to require like a different epsilon or a different amount of compression, just like this graphic that you see on the bottom right.
Exactly.
Those curves are going to depend on data sets. Okay.
Exactly, you're right. But one key observation here is that not only you are doing quantization and pruning and Huffman encoding, but at the same time you are retraining your network. We shouldn't miss that part of the paper, which is nice.
Yeah, that's definitely not on these slides. That seems, would that then mess up all of the quantization that you've done? Because when you retrain, you're going to shuffle things around and they're no longer going to be discretized the way you've done it.
So once you prune it, you retrain slightly, and yes, your weights are going to be different from the original one. And once you do quantization and weight sharing, now all you care about are the centroids, and you can update the centroids this way.
How is that different than dropout? It seems like dropout when training is setting things to 0 and training again and iterating on that process. I guess here it's non-random. There's a pattern or a structure to how you prune versus dropout, which is stochastic.
Yes, exactly. And dropout, you're dropping the activations.
You're dropping the whole node instead of just one connection from it.
Now you're dropping only one connection, one of your weight.
Got it. Okay. Thank you very much.
Sure. Any other questions?